Hello again. Let's take a look at the section 1.5 notes. Again, this is the last section in chapter 1, and it's about infinite limits. So not where we would have a finite limit, like let's say a function approaches 2 or -7, but these are when functions are going to approach infinity as we approach some finite value. Right, so here it says, let f be the function given by f of x equals 3 over x minus 2. If you're thinking, oh my gosh, I have no idea what that looks like, remember this is pretty close to the function over 3 over x that you would have graphed this summer. It's just that it's going to be shifted 2 units to the right. Right, so it's just the same as this, but it's 2 units to the right. Right. So what does this look like? Well, it kind of looks like this. All right, again, we would have to plot some x values and y values to get the exact value. So it's going to be stretched 3 more than what 1 over x would be. So now ours is going to, at 2, right, if we shift over, so here our vertical asymptote was at 0. Now it's going to be shifted over to 2. So we're going to have some sort of dotted line there. All right, if we plug in just a couple values, when x is 1, all right, we put 1 in here, we get 3 over 1 minus 2, so that's 3 over -1 or -3. All right, when x is 0, 3 over 0 minus 2, that's -2 in the bottom, so at 0 it's -3/2 or -1.5. And let's say we plug in -1. So if we get 3 over -1 minus 2, that's -3. So 3 over -3 is just -1. All right, so it looks something like this. Right, and then we could do the same thing on the reverse side. If we have this be 3, all right, then we do 3 over 3 minus 2. That gives us a value of 3. So it's up here. And then at 4, if we do 4 minus 2, it's 2, so 3 over 2. So that's going to be somewhere around here. And based on what it looks like right here, we could just say it's going to look something like this. All right, so then let's talk about what happened. As x is approaching 2, our vertical asymptote, from values that are less than 2, so from the negative direction, what happens to the y values? So we would say that f of x decreases without bound. We cannot stop it, it's just going to keep going. Decreases without bound as x approaches 2 from the left, or values less than 2. And then as we look at f of x as it is approaching 2 from the right, or from values greater than 2, we can say f increases without bound. Again, as x approaches 2 from the right. All right. So the way we would write this is we would say then the limit as x approaches 2 from the left of our function, we could either write f of x, or I'm going to write 3 over x minus 2. We would say this goes to -infinity. And the limit as x approaches 2 from the right of 3 over x minus 2 is positive infinity. So I seem to remember in class a conversation coming up about this where somebody was saying, I think that I read somewhere that the limit approaches infinity, and I said that's going to be true when we start talking about one-sided limits. So here we are, we're at one-sided limits, and now we can say yes. The limit at 2 does not exist, but we could say specifically the limit as x approaches 2 from the left side approaches -infinity, and as it approaches it from the positive side, or from the right, it approaches positive infinity. All right, let's see what that looks like if we do a table. So if you have your calculator and you can put in the function. So I already put mine in. So in y equals, I wrote 3 over x minus 2. I'm not sure if you can see that or not. Hopefully you can. And then I set my window to look like this. My X min was -2, my X max was 5, my Y min was -5, my Y max was 5. And so when I graph it, it looks something like this. So pretty similar to what we have. And then I'm just going to go through and I'm going to use the value function on the calculator to get the values that go in here. So I'm going to say I want value at 1.5. Right, that gives me -6. I'm going to do it again. I'm going to say, what's the value at 1.9? That's -30. I'm going to do, what's the value at oops, I hit the wrong one. What's the value at 1.99? It is 300, -300. I could do what's the value at 1.999. We're down at -3,000. Right, I could do the same on the opposite side. It's going to be symmetric, but now this is going to be +3,000. This is going to be +300. This is going to be +30 and +6. All right, so we say that a limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit. Okay, so let's take a look at some of these examples down here. We've got parts A, B, C, and D. So in part A, we're going to take a look at as x approaches our vertical asymptote right here. So notice how in each case that vertical asymptote, or that spot where there's an infinite limit, it occurs at 1 each time. So we're just going to say how it happens. So in part A, we're going to say the limit as x approaches 1 from the left. And here our function is 1 over x minus 1. Right, I should write that down here. This is f of x equals 1 over x minus 1. I think I didn't include those because it was going to be too much of a pain to include them from a typing standpoint. This is f of x equals 1 over x minus 1 squared. This is f of x equals -1 over x minus 1. And this is f of x equals -1 over x minus 1 squared. Sorry, I hope you can see these. All right, so 1 over x minus 1, 1 over x minus 1 quantity squared, -1 over x minus 1, and -1 over x minus 1 quantity squared. So in our first function, we're going to let the limit as, we're going to find the limit of 1 over x minus 1 as x approaches 1 from the left. All right, so what do we notice in the graph? What's happening? Well, as we're coming in from the left, the function is going down to -infinity. Right, and then likewise the limit of 1 over x minus 1 as x approaches 1 from the right, we would say that it's going towards +infinity. Right, in part B, the limit as x approaches 1 from the left of 1 over x minus 1 squared. Right here, it's going towards +infinity. And then if we repeat the same thing, the limit as x approaches 1 from values to the right of 1 or greater than 1, or from the right side, that also goes to +infinity. All right, in part C, we would say the limit as x approaches 1 from the left of the function -1 over x minus 1. So here, as we approach from the left, the values are going up towards +infinity. And then the limit as x approaches 1 from the right of -1 over x minus 1, this is now going to -infinity. They're essentially just showing us that every combination is possible. They could both go towards +infinity, they could both go towards -infinity, or they could switch. One would go to -infinity, the other go to positive, and then they would switch. One would go to positive and one would go to negative. I'm not going to write D. I think you could probably write that out just like we did here. All right, so So these are the different possibilities that could happen. Okay, on the next page, then here we are, we're talking about vertical asymptotes. Again, we've talked about vertical asymptotes, we've talked about asymptotes together in class last year, and then we're going to talk about here. All right, so if it were possible to extend the graphs above towards positive and negative infinity, you would see that in each of those previous graphs, it becomes arbitrarily close to the line x equals 1. All right, this line is called a vertical asymptote. Oops, asymptote, a vertical asymptote of the graph of x. So again, it gets arbitrarily close to it. That means, like, for example, in one of them, sorry, not x equals 0, x equals 1, all right? Let's say we would have, like, down here, it doesn't look all that close, but as we kept going, we could get as close as we want to this line, x equals 1, all right? Or same thing, we could get as close as we want to this line, x equals negative 1. All right, but it's never going to touch it, and we're going to continue towards negative infinity or positive infinity. All right, so if f of x approaches infinity or negative infinity as x approaches c, in our case it was 1, from the left or from the right, then the line x equals c is a vertical asymptote of the graph. All right, so again, in example 1, the one that we just finished with those 4 graphs, note that each of the functions is a quotient. All right, so that's not coincidental that it's going to happen when there's a quotient, and that the asymptote occurs at a spot where the denominator is equal to 0 and the numerator is not equal to 0. If you remember, we've talked about that in class very recently. So we said if the number in the numerator is not 0, but the denominator is 0, we talked about this relative to discontinuities. We said that this is going to be a non-removable discontinuity. There is a huge tear in the graph when that happens. Versus when we've got 0 over 0, and we say this is where we're going to have a removable discontinuity. We're going to have some sort of hole in the graph, but it's not going to be as horrible as this type. All right, so the spots where we have an asymptote occurs where the denominator is 0, but the numerator is not. This exact case we were talking about with non-removable discontinuities. Theorem 1.4 is going to generalize this observation. So it's saying if f and g are continuous on some open interval containing a point c, if f of c is not 0, but g of c is 0. All right, so again, we've got one time the numerator where where f of c is not 0, the denominator where it is. We're talking about this case right here. And there exists an open interval containing c such that g of x is not equal to 0 for all x that's not c. So again, we've got some point, we've got some little interval around c, right? At c, g is 0, but in the window around it, it's not equal to 0. All right, so c is the only spot where g is going to be equal to 0. All right, so then we can say the graph of the function given by the quotient f of x over g of x will have a vertical asymptote at x equals c. So again, essentially it's describing this situation that we have here. F and g are continuous on some open interval containing c. The numerator is not 0, it's some number. The denominator, some non-zero number, and the denominator is 0. And we're saying c can't be 0 in other places, or g can't be 0 in other places in this window. It's only 0 at c, all right? Then the graph of the function given by the quotient is going to have a vertical asymptote. Again, translation is going to have a non-removable discontinuity at x equals c. All right, so let's find the vertical asymptotes of these functions. So again, according to Theorem 1.14, if we are looking for vertical asymptotes, we're looking for all places where the denominator is 0, but the numerator is not. All right, so we would note here, all right, when x equals -1, all right, again, I'm trying to find places where the denominator is 0. The denominator will equal 0, but the numerator will not. All right, so x equals -1 is a vertical asymptote. I'm just going to write VA, vertical asymptote. All right, what does this look like? It's going to have a vertical asymptote here at -1. Right, for values that are greater than -1, it's going to approach positive infinity as we approach there. And here it's going to approach negative infinity. All right, so just try a value in here. Like let's say we say 0. If we do 0 plus 1 is 1. 1 times 2 is 2. So we're up in this region right up here. If we pick something less than -1, let's say -2, we get -2 plus 1 is -1. So then 2 times -1 is -2. So we're talking about something down in this region right here. Okay, part B. Let's factor that. Here it was obvious that we needed a -1, so let's factor here. It might even be obvious to you at this point. This is x plus 1 times x minus 1. Notice that the numerator is not factorable. All right, it's a sum of squares which doesn't factor. All right, so again, according to this theorem, we're looking for all places where the denominator is 0 but the numerator is not in order to figure out what our vertical asymptotes are. Right, so in this case, we can say that the denominator is 0 at x equals -1 and x equals +1. But since we know this is never 0 because it doesn't factor, then we can say the numerator is not 0. Zero at these points. So x equals -1 and x equals +1 are vertical asymptotes. All right, so what does that look like? Well, here at -1, here at +1, we're going to have vertical asymptotes. All right, just to kind of get an idea of what's going on here, if we put in 2, we're going to get 4 plus 1 is 5, so numerator is positive. 2 plus 1 is 3. 2 minus 1 is 1, so we're going to end up with 5/3. So something like, let's say, right up here. So we can kind of conclude that it's going to look like this. Over here at -2, -2 squared is 4 plus 1 is 5. But if we put negatives in here, we've got -2 plus 1 is -2 plus 1, sorry, is -1. It's late. -2 minus 1 is also negative. So we're going to end up with some positive number up here. So again, it's going to look like this. And then if we plug in something in the middle, like let's say 0, we get 1 in the top and -1 in the bottom. All right. And what that ends up looking like is this. Okay, next page. The top one. Oh, this is a stinky one. All right, so remember cotangent is cosine x over sine x. All right, cosine and sine are never 0 at the same spot. So really what we're looking for places where sine is 0 but cosine is not 0. Again, they'll never be 0 in the same spot. So really all we're looking for is where is sine 0. So looking for places where sine of x equals 0 and cosine of x is not equal to 0. All right, so where are the places when sine is 0? Well, sine of 0 or sine is equal to 0 sine of x equals 0 when x equals 0, when x equals pi, when x equals 2 pi, when x equals 3 pi. So all are integer multiples of pi. In other words, we could say x equals n pi. Right? So there are infinitely many asymptotes. And again, if we could graph this, if this is pi, this is 2 pi, this is 3 pi, this is negative pi, we're going to end up with asymptotes in every one of these spots, vertical asymptotes. And again, hopefully you remember what the cotangent graph looks like. It's like the tangent, except it's going to go downward. I'm not drawing these very well, but you remember it kind of looks like that. Okay. Example 3. What happens when both the numerator and denominator are 0 at some point C? All right, again, we've already looked at that in terms of continuity, but let's look at it again in terms of asymptotes. So determine all vertical asymptotes of the graph f of x equals x squared plus 2x minus 8 over x squared minus 4. So let's factor this. We've got x squared plus 2x minus 8 over x squared minus 4. This factors into x plus 4 times x minus 2. This factors into x plus 2, x minus 2. All right, note our common factors here, which are going to cancel out. And so we're going to get x plus 4 over x plus 2. Again, this is still a point of discontinuity at x equals 2, but if you remember from our conversation, it's a hole. It's not a gap. It's not going to be an asymptote. So when we get to plotting what happens at 2, remember there's just going to be a hole there. It's going to look like this, but at 2, we're just going to put a dot. But notice here at negative 2, right, negative 2 makes the denominator 0, but it makes the numerator 2. All right, so here we're going to say x absolutely cannot be negative 2. There is a vertical asymptote there. So vertical asymptote at x equals negative 2. So we put in that vertical asymptote. All right, we have to see what happens. What's the limit as x approaches negative 2 from the negative direction? All right, we're going to just use x plus 4 over x plus 2. It won't make a difference if we use this or this, because we have a theorem that says that if I can find a function that's the same as our original one, same everywhere except at a certain point, the limit is going to exist and be the same there. So I'll just use this one. As I approach negative 2, so again, let me say something like negative 3 and see what happens. If I plug negative 3 in here, negative 3 plus 4 is 1. Negative 3 plus 2 is negative 1. So this is going to end up being negative, which means that the whole thing is heading in the negative direction. So this is going to go towards negative infinity. And limit as x approaches negative 2 from the right of our function x plus 4 over x plus 2. All right, I pick something that's greater than negative 2. I want to pick something that's close to it, so I'm just going to pick negative 1. All right, I don't want to get way over here because then who knows what's going to happen. I just know that at this point it's got to either be approaching positive infinity or negative infinity. So I want to be close to that so I can see what happens. So I'm going to pick negative 1. Even better would be if we picked negative 1.5, but I'm just going to go with negative 1. So negative 1 plus 4 is 3. Negative 1 plus 2 is 1. So this is going to be 3 over 1, which means it's up here. So that means it's going to approach positive infinity here. All right, I have not drawn this very well, but what happens is at 0, I get 2. So let's maybe work on doing this a little bit better. All right, so at 0, it's 2. So maybe we could say this is a better start to our graph than what I had there. And then at 2, all right, again, this function is not defined there, but at 2, I can say, well, that is, the numerator is 6, the denominator is 4, so that's the same thing as 1.5. So at 2, we're going to have a hollow dot right here at 1.5, and then it's going to keep going down like that. Okay, I think I'm going to stop there, and then we'll pick up here in class. All right, hopefully you were able to see all of that. Bye.